What are some of the astronomical implications of Newton's law of universal gravitation? A great example is orbits. An object in orbit around another is technically just falling but continually failing to land upon the central body. This is Kathy. Kathy stands on the Earth with a red ball in her hand. Gravity wants to pull the ball towards the center of the Earth away from Kathy's hand. This gravitational pull is represented by the blue arrow. Now, Kathy is strong enough to throw the ball with such force that it ends up in outer space. According to Newton's first law of motion, this ball should travel in a straight line with a constant speed. This potential path is represented by the purple arrow. However, the ball is still under the effect of the Earth's gravitational pull. So, despite it wanting to go forward in a straight line, its path is altered a bit due to the Earth's gravity, and it ends up following a new path, represented here by the black arrow. At this point, the ball will continue moving along the straight black line as per Newton's first law, but gravity is relentless. It still pulls on the ball, trying to pull it down to the center of the Earth again. So, the ball has yet again a new path. As the ball continues to move, it is experiencing a constant battle between its own tendency to move forward in a straight line and Earth's gravitational pull trying to pull it down to the center of the Earth. This continued motion eventually results in the object going into orbit around the Earth. So we can say that an orbiting body is falling but continually failing to land. But here's the interesting thing about objects in orbit. It's not that one object orbits the other while the other stays completely still. They both move. They just happen to revolve around their common center of mass, which is called the Bary Center. The Bary Center of these orbiting bodies is represented by the plus sign near the central object's orbit. The Bary Center of a system of identical masses is right in the middle of the distance between the two masses, but if one of the objects were to become more massive, then the center of mass would move closer to that more massive object. The Bary Center of the Earth-Moon system is physically located within the Earth itself. So when the Moon orbits around the Earth wobbles in place a little bit. Here we can see a very small mass orbiting a very large mass, much like the Earth orbiting the Sun. The Bary Center of this system is embedded deep within the larger mass, so its wobble is not very pronounced. Here, however, we have two objects somewhat more comparable in size orbiting each other, like the Moon around the Earth. The Bary Center in this system has moved towards a point that's more central to the two objects, and in doing so, it has moved closer to the surface of the larger mass. The mass difference is still too drastic for the Bary Center to be literally in the middle of the two objects, so here we can definitely see a more noticeable wobble. In fact, when we think of our own solar system, the planets don't actually orbit the Sun. Rather, everything in the solar system, including the Sun, orbits the solar system's Bary Center, whose position has actually been changing with time as the objects continue to orbit. Some examples of the rather tangible astronomical implications of these orbiting objects include, first and foremost, tides. No, not these tides. These tides. Earth's oceans and lakes experience tides as a result of the Moon gravitationally pulling on the Earth. And since liquid is more easily manipulated than the Earth's crust, these tides are clearly noticeable in bodies of water. The tides on Io, the innermost moon of Jupiter, are so strong that the rocky surface sometimes stretches around 200 feet. This animation is not to scale, but it gives you a sense of what the planet experiences. And in fact, because these tides are so strong, Io undergoes a process called tidal heating, which keeps the rocky interior of the moon molten and feeds its surface volcanic activity. In an evolved binary star system, like the one shown here, tides can rip the outer gases right off of an evolving star.